ask questions, please. It's a very important piece of this sort of the day. So,
and interrupt me as I go. If I don't see your hand up, just shout, "Hey, idiot!" I'll answer.
So this is Dominick, Rocco, and he's from the University of Minnesota, and we're lucky to have him here today, and I'm going to let him introduce himself in more detail as far as the research he does. By the way, for those of you from Mounds, I'm Shane Wood, Mr. Wood, and I'm one of the physics teachers over here at Irondale. And
Irondale people, my name is Mike Cartwright, and I'm doing Shane's job over at Mounds.
So, welcome everybody.
Both of you guys are great. I'm happy to be here because I think it's really cool that this thing can happen in high school. How many students are there here? 9 through 12, right?
1,600, 9 through 12, in both buildings? Is that
Yeah, about 1,700 Mounds. You were close.
So, yeah.
Okay.
So, about 400 per grade.
It seems really expansive. You know, you guys must have plenty of space to spread out.
Well, this is a very sort of a one-dimensional building. And
Oh, is
very
that it? I just
flat.
have to walk
I guess
really
two
far to
dimensions,
get
right?
front to back.
Yeah, and so it's just like they added on, added on, added on, added on. And since this is not in like down from New York City or something, it wasn't vertical. It's
Right.
very spread out. So we actually are very tight on space, even though it's a.
Even though I have to walk a mile.
Yeah, and that actually, for some other time in the future, I would encourage you to park up by the tennis courts here. It's like just a few meters away from the street here. So there's anyway.
Gotcha.
Conversation for a different day. But.
Right. But okay. So I'm a graduate student at the University of Minnesota. Says pointing. I've been doing it for over 4 years, which means I'm a 5th-year grad student, although it's hard to admit. I hope to be graduating with my PhD at the end of the year, which is exciting. And you can ask me at the end what I plan on doing after this. How many of you have met me before? That's really awesome, because I'm not going to double think myself. But I'll be honest about that later. So I've been doing this for quite a while. I started working on NOvA in 2010. NOvA is a neutrino experiment. And before I get too far into it, I should start at the beginning. So I think some of you are taking a particle physics class here in high school. Is that right? Just a few of you. So raise your hand if you are taking that class. Oh. So most of you. So if you've already learned this in your class, I'm sorry, I'm going to repeat it, but hopefully my perspective adds a little bit. So the Standard Model is this thing, and it lists all of the particles that we know about. And the definition of particle is a little bit broad. That doesn't mean that this Standard Model is right, and it doesn't imply any truth to it. It's just sort of what particle physicists can agree on, that this is what we've established. Okay? It only lists fundamental particles, which means they're not made up of other particles. And it tells us that there's a type of particles, or a classification called quarks. And they make up protons and neutrons, as well as other things that you might have learned about, like pions and kaons. Okay? So the protons and the neutrons are made up of the up and down quarks, right? And pions as well. And then when you start adding other quarks into the mix, or you start adding more energy to those particles, you get all kinds of other crazy stuff. Okay? And that's what happens at the LHC. We take protons and smash them together, and we add energy to that system, and we might reconfigure how the quarks are arranged, and all sorts of stuff shoots out. I always liked a description of those interactions as, I'm going to hand wave for a moment. But the interesting thing about quarks is that their attraction, like most attractions, depends on how far away they are apart. But instead of that attraction shrinking, like the electromagnetic interaction, that interaction gets weaker as they get further apart. For quarks, the strong interaction grows as they get further apart. So if you take these things, which is a lot like what happens when you stretch a spring, actually. So imagine you've got particles tied together with a spring, and you start pulling them apart. The thing that's pulling them apart might be the fact that they're wrapped up in some other proton, and as they come together and collide and pull, right? But as you pull these quarks apart, the force between them grows, and you keep pushing and pushing and pushing, and you're putting energy into that spring or into that bond. And you're pushing and pushing, and at some point, you can take all that energy that you just put in and convert it to mass. And it turns out that you can get to a point where the mass that you would put in the middle to make 2 new quarks is cheaper than all of the energy you just put into it. And so 2 new quarks pop into the void for each of the original quarks to be bonded to. And you end up with new particles because you just sprung mass from the void because you put so much energy in to buy it effectively. And now you've got these new particles traveling away. And then what particle physics does is it studies those interactions, and a lot of people say it's like, what, reconstructing a car crash, but all that you have is, the tire tracks on the ground and some busted up cars on the side. So anyway, so those are the quarks. That's not what I study, so I just wasted like 10 minutes talking about what I don't do. The other type of particle is, so another type of particle is the leptons, right? Now the electron is one that we're really familiar with, okay? But it also has heavier relatives, cousins I guess you'd call them, called the muon and the tau. And those 3 guys are charged. The muon is only different from the electron in its spin. Its charge is the same, the muon is only different from the electron in its mass. Its spin is the same, its charge is the same. But it's 200 times heavier. And then the tau is another 1,000 times heavier, another 10 times heavier than that. So the electron has these 2 heavier cousins, which actually decay to electrons. So if you leave a muon around long enough, it turns into an electron. And that's because mass and energy are the same thing. The muon's higher. Things tend to want to shed their energy, just like this paperclip wants to fall down and get rid of its potential energy. Fell in the trash. Sorry, I threw away my paperclip. Anyway, since things want to shed their energy, muons decay to electrons, and taus to muons and electrons, all the same. Okay. Now, all of those things, when things decay, those are interactions. And interactions are mediated by the bosons. So when I say that something interacts via the weak force, I mean that one particle sent a W boson or a Z boson, which mediate the weak force. It takes this boson, it sends it over to the other guy, and sends something to it. So the bosons can sort of carry a property of a particle, like a charge or some mass or some energy, to another particle, and that's an interaction. The cool thing about this is that gravity was conceived of as this long-distance force, that it could make things fall from a distance. And you have these electromagnetic interactions, which do the same thing with a photon. They send a photon to communicate some information. And it always puzzled physicists that you could have these long-distance interactions. And what particle physics tells us is that they're not, in fact, long-distance interactions. All of the information is carried by another particle, which is a boson. Okay? So that's the standard model. This is what we can agree on. Oh, I didn't tell you that each of this electron, muon, and tau, those guys have a cousin, as each of them has their own cousin, called the neutrino, which is neutral. But the electron neutrino is like the electron, muon neutrino is like the muon, except they're neutral. The fact that they're neutral, I should tell you, the quarks talk to the gluon, which is the boson that carries strong interactions. And strong happens a lot. The quarks also talk to the weak bosons and the electromagnetic bosons, but less often, and less often means they're weaker forces. The W and Z bosons are much weaker than the photons. When I say weak, it's the probability that they will interact. Now, the leptons will talk to the W and Z bosons as well as the photons because they're charged. So they'll interact weakly and electromagnetically. The neutrinos are not charged, so they only interact through the weak force, which means they interact very rarely, and that makes them hard to observe. Okay. So neutrinos were conceived of when physicists studied beta decay 100 years ago. And since neutrinos interact very seldomly, you can't see them in most experiments. And so this beta decay, where a neutron turns into a proton and an electron, all they can see is the proton and the electron. Okay? Now, you can work out a simplified, not so simplified, but you can work out a model of this where you're going to have some amount of energy liberated, and that has to be shared between, if what you see is a proton and an electron, the energy has to be shared between them. Since the proton is really, really heavy compared to the electron, after the decay, it should remain roughly stationary, right? And so you should observe most, and you get that by conservation of momentum. And so most of the energy you should observe going to the electron. So you should be able to know, for a given nucleus, when it decays, you should be able to know precisely what that electron's energy will be. So they went to measure that. And if you try to measure that, it means, ooh. Do we know what a histogram is?
Yes.
Okay. So in a histogram, you count up the number of things with a given energy. That's what we're looking at here. Well, we're not seeing individual bins, right? But we're seeing a smooth approximation of one. Now, what you expect to see for this beta decay, where you know the energy is just a line, where everything has the same energy because you know the electron energy. What they actually observed was this smooth distribution at a lower energy. Okay. And they didn't know what to do. This was a huge problem because it meant that conservation of momentum and conservation of energy weren't working. And physicists really liked conservation of momentum and energy and had gotten them so many great results. So what Pauli said was maybe there's a particle we can't see. And he later went on to say, I've done a terrible thing. I've invented something which cannot be detected. And then Fermi called it the neutrino, which means little neutral one. But Pauli was wrong, because in 1956 they did manage to observe neutrinos. Now that we've been observing them for a long time, we know some things about them. We know that they're very small. They rarely interact with ordinary matter. Billions of them are passing through you right now. They come from the sun, they come from other galaxies, they come from the Big Bang. They're passing through you right now, and you don't even know it. They just slip right through. Because if an atom were blown up to be the size of a football stadium, the nucleus would be tiny. It'd be the size of a football in the middle. And the electrons would be even smaller. They'd be like golf balls out in the stands. And I might not have that golf ball right. They're probably many orders of magnitude smaller than the football. But they're hanging out in the stands. And the intruder comes in and it just slips through that stadium completely undetected because it never interacts with any of the particles. Takeaway, you're made of mostly empty space. And I always found that really interesting. That empty space happens to be filled with electrons which repel each other, which sort of act as a cradle for a nucleus. And that's kind of cool. Okay, and further, those neutrinos could travel through a light year of lead and probably not interact. Light year of lead is a lot of lead. They do rarely interact, though, if if they get close enough to one of those electrons or one of the nuclei, they can exchange a W or a Z boson and leave a trace. All right. So as we've observed them, we also have noticed that they change form as they travel, and this is called neutrino oscillations. This means that what starts as a muon-type neutrino could transform into an electron-type neutrino, or a tau-type neutrino. And the probabilities change, the probability of that transformation changes based on the energy of the neutrino, as well as the neutrino energy. And if you're curious about these transformations, I can try to paint you a nicer picture of why it happens. So ask me about that if you're curious. Okay, so I work on an experiment which tries to study these interactions and study those oscillations. We are particularly trying to measure the probability of one type of the muon neutrino oscillating into an electron neutrino or a tau. Actually, it doesn't. We don't see taus because our neutrinos are too low of energy, and taus are too heavy. So essentially, our neutrinos are below the threshold. Our neutrino energy is below the mass of a tau neutrino. Or sorry, our neutrino energy is lower than the mass of a tau particle. So a neutrino can't create a tau because you don't have enough energy to make one of those things. So our experiment has a terrible nested acronym, which is just awful. And try writing an introduction or an abstract when you've got an acronym and an acronym. But neutrinos at the main injector is a high-intensity muon neutrino source at Fermilab. The NUMI off-axis electron neutrino appearance experiment, or NOvA, puts two detectors in that beam line. We put one at Fermilab, a kilometer from the beam source. We put another one in northern Minnesota, as close as we can get to Canada while we're still on US soil. And really, we just wanted this to be as far as possible. And one of the professors at Minnesota happens to be in good with one of the Parks guys, so we can put it in Minnesota. Anyway, so that far detector is 810 kilometers from the source. Right? So the beam, I think, is really neat in itself, although I don't work on it. It's created by taking high-energy protons from the main injector at Fermilab, which is one of the pre-acceleration rings from the Tevatron days. The Tevatron was the thing before the LHC that was the biggest machine in the world. It's since been turned off because the LHC is doing so much better. But the pre-accelerator rings are still very much in use. So we take protons at 120 GeV. GeV is an energy unit. It's for giga electron volts. And we take those and we slam them into a target. So you take this really energetic beam and you slam it into this fixed target. And those protons interact with nuclei in the target. And that creates a shower of other particles. Those particles are not neutrinos. They're charged, mostly pions and kaons, which are made up of quarks, like we talked about before. And the cool thing you can do is you can take that nasty shower of charged particles and you can focus it. And you can actually attempt to, you can steer those charged particles into roughly a beam. And you can also select, using your horns which focus the particles, you can sort of select an energy range and a particle type. And so what we try to do is we try to focus the pions and actually defocus other particles like kaons. And the reason we want the pions is that when the pions decay, they almost always decay to a muon and a muon neutrino. And those muons can be absorbed downstream. So here, if you just trace the lines, you've got a green line coming in. These blue lines are the pions. And after they're focused, they go into this decay pipe, and then we get a muon and a muon neutrino. The muons are charged, and we can absorb them in some rock downstream of the beam. But the neutrinos, once you make them, they're gone. They're going. You can't do anything to steer them anymore. And considering how elusive neutrinos are, I really got a kick out of this when I learned it. Because to take something charged, like that you can control, and create something that you can't control, I think is really neat. All right. And so we get this intense beam. The beam isn't continuous. It's one pulse every 1.5 seconds or so. And each pulse contains, right now it's 2.5 times 10 to the 13 protons. And the design is twice that, or more. But Fermilab's working on making the beam better. Okay. Now, the NOvA detectors, these are the things that are placed in the beam line. There's one 1 kilometer away and another one 810 kilometers away in northern Minnesota. They're really neat design, and I'm going to talk through that design. The field of particle physics might never build another detector like this ever again. And lately I've come to realize that that's a shame, because the things we're doing with this detector are really amazing. Now, I have some pictures here which will kind of get the point across, and I'm going to try to complement that with what I have in front of me. So, the basic unit in the NOvA far detector, now the far detector is the big one. The near detector is a smaller version. It's not a scale model because the bits are the same. I'll get to that. Okay. So the near detector is just smaller. It's the same thing but smaller. Now, the fundamental unit in the NOvA detector is a cell. It's a 50-foot long square tube, and it's filled with a stuff called liquid scintillator. Does that word ring a bell to you guys? Or does scintillator ring a bell? Scintillator is, can someone tell me what scintillator is in your words?
It's like this magic stuff that lights up, right?
Why does it light up?
It's magic.
No, but what causes it? Does it just light up willy-nilly?
Oh no, when particles hit.
Right. So when charged particles are moving around, then the charged particles we observe in detectors are the ones that move around close to the speed of light. But as they move around, they actually will interact with the electrons in a material. They'll ionize it slightly, they'll knock some electrons around, knock some away. And scintillators are special in that when those electrons get knocked around or recombine with an atom, they emit light. Okay? So you can use scintillator to view particles, and that's pretty neat. So scintillator is a very special material that lights up when charged particles pass through it. And liquid scintillator is a liquid form of that. Other experiments use plastic scintillator, which is really nice because you can take some plastic and put it there. NOvA uses liquid scintillator because we want to build these long tubes and then fill them. So we actually have a blend of mostly mineral oil and 15% scintillator. It's this stuff called pseudocumene. They're usually these big organic molecules with a bunch of hydrocarbon things. And I think they typically have rings in them, like benzene style rings. Do you guys know any organic chemistry? No? You'll hate it in college. So anyway, so we can get this light out of the scintillator, and that's great. And what we do is we run this fiber down the cell. This is called wavelength shifting fiber, and it's different from the fiber used in telecommunications, but it's an optical fiber. And the thing that makes it different is that can you see there that it's kind of glowing at the tips? That's because it collects the light from the edges around the whole length of this fiber, and it's designed to trap that light and shoot it to the end. So any light that hits this is designed to shoot to the end. Okay? So we take that, we run it down the cell and back, and it's dark in there in the sealed detector. So when a charged particle passes through it, you get a little pulse of light that zigzags up to the end of the cell. Any questions on that so far? Now this is a cutoff of one of those modules, or of a module in the detector. I haven't used that word yet. So I said that the basic unit is one of these long PVC tubes, and you're looking down 32 of them as I show this to you. All right, and they're 50 feet long, so they run. If I'm holding it like this, it runs to the back of the room, or way beyond it, 50 feet. Okay, and this is the end where we attempt to read out that light. I shouldn't say attempt, we do pretty well. And what it does is, you saw the fibers as I showed this to you. All those fibers take a turn in this black manifold here. And they come out to the end, and you can see on this end there's 32 different green dots. Okay? And we slap a bit of electronics on there. They can read out one of those dots separately. And each dot is actually both ends of the fiber that goes down and back. Right, so it goes down 50 feet, makes a turn to 100 feet long. We slap a bit of electronics on that, and each one of those is called a pixel, or each little bit that reads out one of the cells is a pixel. Just like in your camera, when you hear about megapixels, it's because there's an array of light detectors, and each individual light detector is called a pixel. And so we put that on there, and we can take the signal from this electronics and digitize it and store it for later. And we can actually say when a particle passes through a given cell. Okay. Now what that allows us to do, what I haven't told you yet, is that these things are 50 feet long, and we take some of them and we run the tubes horizontally. And in the next plane, we run the tubes vertically. And then we have another horizontal one, another vertical one. We build these up. The horizontal guys give you the Y position of a particle if it passes through it. And the vertical guy gives you an X position. And then which module you have a hit in can give you a Z. So you can get a 3D picture of particles passing through your detector. And what we want to do is see particles coming in. So here would be a neutrino coming from Fermilab. And it comes in, it interacts, and out comes a charged particle, some other charged particle, another charged particle. And from the hits it leaves in the detector, we try to reconstruct some lines, and then we actually use the amount of light it deposits, which corresponds to the amount of energy that it deposited in that cell, to learn something about the particles. So different particles will deposit more or less energy depending on what they are. Muons tend to deposit a little bit of energy really consistently, so you can identify a muon. Whereas a pion will deposit a lot more and is a lot more likely to take like a hard right because it scatters with the nucleus. And so you can use those characteristics to identify specific particles. That sort of detail is what's really unique about NOvA. We've never had a neutrino experiment with a really big detector that's able to determine fine-grained features like that and identify particles. Okay. Now I told you guys the FAR detector is really big. So I said the modules are 50 feet long. We have some horizontal and some vertical. So it's 50 by 50 and 200 feet long. This is something that you would struggle to fit in a basketball gym. And you could probably fit it pretty nicely on a football field. It's big. If I click this, will I get a browser?
You should. Well, if it's
It's not a.
Oh no, it's just
I
because
can
it's not
pull it up
blue
on the
doesn't mean
side
it's not a link. It's definitely a link.
oh here. The document is trying to connect to.
Oh yeah, it thinks it's a virus.
It's a virus.
Allow it?
Yeah, so the weird thing about PDFs is that they can execute arbitrary code, and you call that hacking. I don't know why Adobe built this into the PDF standard, but yeah. Yeah, this is what I want.
You want volume?
No, we don't need that. And I'm gonna try to fast forward through it.
Okay.
Okay, so here's them building the FAR detector up in northern Minnesota. The cool thing is all of these modules were assembled at Minnesota. You see them going that way, Now they're putting in verticals, now they're putting in horizontals, verticals, okay? They're laying them down on this giant thing called a block pivoter. And the great thing about this is you get a sense of the scale because there's people right there, okay? The cool thing is all these modules were assembled right here at the University of Minnesota by undergraduates. And the University of Minnesota might get to build another detector for another experiment at Fermilab in the coming years. So if you go to the U, you could actually work on that.
And this is the third one, right? Because there was the Minos detector, that piece that's built there by students.
Right, although they split that labor with, I forget if it was Berkeley or something, and Berkeley wasn't allowed to do it again because Minnesota did better. So, you know, Minnesota sort of had this is a great thing for the university. It brings in money to the university. It's amazing. And so the opportunity is really world class and unique. I saw a hand up.
Yeah, how many fiber optics are in each PVC pipe?
So each tube has one length, or one piece, which runs down and back. So it goes 50 feet away and 50 feet coming back to be just over 100 feet long.
It's filled with liquid.
After you run that through the cell, hold on, I want to pause this. They painted it. This is the really cool part, but I want to get to that later. So after you build it in Minnesota, you run the fiber, you put it on a truck. Fun fact, they're 50 feet because 50 feet fits on a truck. You know, you think you can design whatever you want, but you have to design it within the parameters. Did you show them, you should show them how they moved that there's the Muti experiment, and they moved the ring from Fermilab, or sorry, from Brookhaven to Fermilab.
We've not seen, we've not looked at
You
that.
should show them that sometime. So, and that was really exciting because this ring got to roll through town and people got excited about particle physics. Anyway, so you put it on a truck, right? You ship it up to Ash River, where the detector is, and then they assemble it into this block. And then they move it, we're about to watch that, and then they fill it. And then they put electronics on it. We'll get to all that. Okay, so this thing, it's 50 by 50, you saw a person standing on that. Once it's full, it's hundreds of tons. And there's this very special machine that moved it through the detector hall. And this, the first time they did this, it took a few days, because this is a custom machine that was built at Fermilab. It's moving 569 metric tons. Okay? And this took a few days the very first time, and I think this is the first one. So you see some pauses in the time lapse here. Later on, they were able to do this in a few hours. Really impressive. So this whole thing, I think it just made a big jump down the hall. Above it there, this is the access platform that they use to install electronics and do other things. Why are they rewinding this stuff? Well, they got there, and look, there's the first detector block standing in place. There's the team that did it. Great guys, Minnesotan, hardworking.
Advertising
No,
for
it
Minnesota
is,
labor.
you know, it's a good advertisement, but it, you know, it's a testament to what you can do with a well-organized team of people. Wow, my perspective is a lot different than it was last year. I think I was a lot more jaded a year ago. Now I see the light at the end of the tunnel and I'll graduate. So here's about 7 of those detector blocks with electronics installed. And at this point we were still installing another, this is only half the detector, we still were halfway to go. But we already had these blocks filled and instrumented, and we were taking data and looking for neutrinos in there while the detector was being built. And that's another really cool thing about this experiment is as soon as we got the first component ready to go, even though we were still working on it, because it's big and it takes time, we were already reading out the data. So here's the far detector. It's 50 by 50 by 200. Here's the near detector. It's in a cavern underground at Fermilab, because the beam is actually aimed underground, and if this is a cross-section of the Earth, here's Fermilab, and here's Minnesota. To get the beam to get to Minnesota, you actually have to aim it underground and have it skim a chord, the geometry chord, and then emerge on the other side. And so the beam travels under Wisconsin and through some northern Minnesota basements, and then emerges and ends up. And by the time it gets to Minnesota, it's 25 miles wide. The interesting thing about NOvA is that it's off-axis, because there's a funny thing about pion decay that the neutrino energies are more consistent off-axis than they are on-axis in the beam. Question? Okay.
We have a lot of struggles with I use that all the time for modeling the CMS detector. Because that's
Oh, really?
the detector that we often use.
Right.
That many of the students are analyzing data from. And so it has a nice built-in beam pipe and everything. So
That's awesome. So I'll say that the CMS detector is admittedly more finely grained than NOvA. Right? The finer grained your detector is, the more precise information you can pull out about the particles. And so I'll admit that most parts of CMS, the muon tracker might be more or less finely grained. But most parts of CMS are small bits. And so that lets them get a more detailed picture. But our detector's big. And CMS is pretty big too, but it's just different. And our detector was a lot cheaper than CMS. Okay, so here's the near detector. It's a lot smaller. There's not a person here for scale, but a person would. That's a railing, so there you go. That's a railing for humans. So there's me. There's a human for scale. So I was there at Fermilab a little over a year ago, helping install electronics and whatnot. Now here's some real data. Any questions about the detectors before I move on?
The scintillator's organic, you said?
An organic molecule is something that's made of carbon and hydrogen and some other things.
So if you ate it, would you get energy?
No, you get really sick and die. So sorry, I use that term. It might be a college level term, but organic molecules are hydrocarbons and anything that. Carbon is really special for a lot of reasons, but carbon has the ability to make 4 bonds. It's the lightest thing that makes 4 stable bonds. And that means it can be used to build all sorts of things. So since it has these 4 bonding sites, you can put 4 hydrogens on it. And that's called methane. And we use it all the time. And if you take 2 carbons bonded together and then put hydrogens on the rest of the sites, you get propane, I think. In chemistry in college, you learn how to name these things. You know, it's a whole. It's considered a separate branch of chemistry because there's so much. It's so important. So you know.
So you can't eat it.
Well, I mean, it's actually quite. Our scintillant is pseudocumene. It's called, and it's quite toxic.
So the organic food movement is a more recent
Organic.
it's a more recent use of the word organic.
Right.
It is not the same as the word organic in chemistry.
And scientists like to poke fun at it, actually.
Right.
Like, well, all those chemicals they're putting in there, they're organic too. Anyway, I'm not going to make fun of chemists too much.
Hey, Dominic, how does the detector at Ash River compare, the NOvA detector compare to the one in the Sudan mine? And what can they detect differently?
So, can I come back to that at the end when I know that I have time? There's a few differences. One of the primary ones is that there's 6 inches of steel and then a 1 centimeter horizontal plane and a 1 centimeter vertical plane. That means most of the detector, that steel, and the reason they did that is because neutrinos are rare, and they wanted all that mass, the steel in there, because the higher density material is, the more likely you are to catch a neutrino. And they thought, you know, these experiments get built to measure parameters before they know what the parameters are. And they thought that these oscillations were going to be a lot more rare than they turned out to be. So they built a detector that could observe as many interactions as possible, but not necessarily measure their energies well, right? So you have this detector that's not very finely grained, and it can't measure energies very well, but it's designed to catch a lot. It turned out that, it turned out that it was easy to measure the parameter they were trying to measure, and they got a lot of events, but they ended up becoming what's called systematics limited. So when you do an experiment, you have statistical error and systematic error. Their big systematic error is energy resolution. And they ended up getting so many statistics that the statistical errors got really small, but that energy resolution systematic doesn't get small. And so in the early years, experiments are always statistics limited. And then once they get past a certain time, it's usually not worth running them anymore because the systematic errors are staying the same. And so it's really interesting. You design experiments, you run, and in the early years, you're just trying to get events. And then in the later years, you're trying to really understand as much of those events understand as much about those events as possible so that you can beat down your systematics. There's other differences between NOvA and MINOS. The on-axis, off-axis thing is a primary one. So I don't have the plot. That's not a real marker. Fuck it. Okay. So I said I'm just going to get to it. What's my timeline?
6-ish, 6:15.
Okay, I think I can hit that. And we might run to 6:15 on question. If you guys have to get up and leave, I'm not going to be offended. But if we made a histogram of the neutrino energies in the MINOS detector, here's so this is GeV of the neutrino interaction. And here's 2 GeV. The oscillations occur around 1 GeV. Okay, and then if I scale right, this is like 10 and so on. 20, okay. In MINOS, which came before, the energy spectrum of neutrinos was kind of like, let's try to get it roughly right. It's kind of this big mountain. They were interested in this, and they got all this stuff here. Well, they might have been more interested in like here. That's important. The NOvA energy spectrum off axis, because of that funny pion decay thing, is more like this. Okay, and you say, well, that's fewer events total than what you get in MINOS, but they're at the energy that you want to study. Okay. Now, those are before neutrino oscillations, and what we actually observe is something like that, because the neutrinos in this region have oscillated from muon type to electron type. The other interesting thing is that when neutrinos interact, they might produce the lepton that they're associated with. So a muon neutrino might make a muon, and an electron neutrino might make an electron. Or it might become, or it might stay a neutrino and just deposit some energy. And then the neutrino leaves and carries away some of that energy. So it just has an interaction, it exchanges a Z to deposit some energy. The Z is neutral, so the neutrino doesn't change its charge. And you get this little shower of energy. Sometimes those neutral current interactions can look like the charge current interactions. We actually want the charge current interactions. The neutral current ones that we don't want, the neutrino leaves and carries away energy. So a neutral current that happens at this energy, and the neutrino carries away some of the energy, will look like an interaction at a lower energy. And that's called feed down, and that was one of the big systematics in MINOS, was high energy neutrinos feeding down. NOvA has less of that problem because we don't have a really long high energy tail. And this is a lie, of course, it doesn't go below 0. In reality, it looks like this, and you have this sort of long high energy tail which comes from kaons. That can be a good or a bad thing because we still do have some feed down. And also, but it can be a good thing in that we can, since no oscillations occur out here, we can use it to make sure we have our simulations right. Okay, I'm going to jump back into this. This is what happens if you, this is what it looks like if you turn on the NOvA detector for 500 microseconds and turn it off. And that's called triggering, something I won't talk about. We do that trigger process every time the beam pulses. So here's your 0 to 500 microseconds. All the hits we recorded in the detector are colored by time. Okay. So here's the color scale. Up here is the X versus Z view. This is what you get from vertical modules. Down here is the Y versus Z view. Okay? So this is your up and down. This is your east and west. Okay? And then this is your north and south. The Z is this dimension. The event display, this is the charge or the amount of energy deposited in each cell. And it's histogrammed. And our event display has this option where you can color by charge, and I'll show you that later. And then it always tells you, so that you can't screenshot this and lie, it always tells you some basic information like when the data was collected and what experiment you're on.
Do people screenshot and lie a lot?
People screenshot a lot, but not typically for the purposes of lying. But it's really so that if you forget to write it down, you know, it's good science, right? It's like putting that entry in your lab notebook for you, right? Now, what you see here is noise. There's kind of just a brown dim throughout the whole detector. And then there's these lines. Those are cosmic rays. The FAR detector is on the surface. There's a ton of cosmic ray background. Now, the beam peak, or like the beam pulse, actually happens in just 10 microseconds in the middle of this. So, you know, if you just limited this to 10 microseconds, you'd probably see one or fewer cosmic rays. But cosmic ray background is a huge problem for us to solve in NOVA. Okay. Now that background itself is really interesting. Here is a coincident muon shower. So some high energy thing happened up in the atmosphere, and it rained a bunch of muons concentrated right on the NOVA detector. You see all these the parallel lines as the muons come in. And those are really cool. We have a trigger that's actually really good at picking just those out. I mentioned that we trigger on the beam, and that's just sort of it's a known trigger. You know you want that data. It's also a big field of NOVA these days to make data-driven triggers, where you look at the data for some sort of particular shape and you trigger on it. Okay. Here's another really cool thing. This is some giant, probably neutron or something from cosmic ray background. These things happen all the time, like, you know, a few times a day. And you get these giant energy distributions that just rip through the detector and just leave a huge blob of energy. Okay, now here's what we're looking for. Here's a neutrino candidate from the FAR detector. It's just a beautiful one. What people think this is. Now, we haven't run our fancy algorithms over this yet, because we do what we call blind analysis, where you don't look at your physics and the energies that you're trying to measure until you know everything's in place. But we have run searches just to find neutrinos to make sure we can. And we find them with just basic cuts like, do you touch an edge of the detector? You know, if you draw a line, does it touch the edge of the detector? Or two edges. And if it touches two edges, it's probably a cosmic ray that ripped through the whole detector. But we find neutrinos often by finding things that don't touch edges of the detector. Here's an example. So what we think this is there's a nice long muon track, because muons deposit their energy slowly and gradually, so they can make nice long tracks. And then here you've got a nice proton track, and you see that there's sort of more jaggedness to it. And here's a nice little hard scatter where it turned. And then at the end, it might have decayed or something. Or, taking another hard scatter.
So now, when you said from one edge to the other, you mean, is it from like the top to the bottom, or from the...
So this guy is a neutrino coming in, and the beam direction is horizontal, right? So the beam direction is north to south as we go this way. And like I said before, this is your up and down, and this is your east and west.
And one reason I'm pointing this out is because there are some students who are looking for cosmic ray data from the CMS detector, and so there's a similar logic to looking at the path of the well, they're looking for cosmic ray muons coming into the detector, and so knowing the path and seeing if it's a path that's not possible to have come from an interaction inside of the CMS.
So if you miss the beam pipe,
right,
then you're probably a cosmic ray muon.
Exactly. And so just making that link for some of you who are working on that as well. For what it's worth.
yeah, you know, you should talk to Dan and probably a student that's not me. But there's so much data in NOvA that we could probably release to the public, and maybe Dan, you know, Dan's still doing QuarkNet, right?
Mm-hmm.
So, you know, it would be really nice if we could get that out somehow.
Yeah. In fact, some of the people here will be going to meet Dan and et cetera on the 28th of March. We have that master
He
class.
hasn't told me yet. He'll
thing.
probably try to
I
drag
just met
me
with
in.
him on Saturday, and he brought up your name, and so did I. So you might hear from him.
We'll see how it goes. Yeah,
I know you're busy, but
I'll probably be involved. Assuming I'm not traveling, I have to check that. Okay, anyway, so this is the part here. These are rare and hard to find. We found tens of these in the last year by looking, not really hard, but looking kind of hard and just making sure we can. And actually at first it was really hard. And I told you the detector was small in the beginning, and so a big thing that I did in the last year was just to look for any like hint that we're actually triggering right and seeing neutrinos. And I did it by looking for interactions that happen in front of the detector, and just the muon makes it into the detector. So essentially what I looked for was nice straight tracks that started in the front and made it some distance into the detector. And that ended up being the first statistically significant evidence that we were seeing neutrinos in the far detector. So that was exciting. But they didn't look pretty. They weren't nice like this where you see the vertex of the interaction. Now in the near detector, you're near the beam, and it's so intense that you can just have neutrinos like candy. So here's a nice interaction in the near detector. This is one of those, what we call rock events that I was describing before, what happens in the rock in front of the detector and just the muon leaks in. And then here's a nice contained neutrino interaction in the detector. Again, colored by time and zoomed into the 10 microsecond beam window you can see. Here's another one. And when I talked about what NOvA can do that other detectors couldn't, this is 6 centimeters, one of these cells. It's this guy here. And Minos had that much steel and then just a little bit of active material, right? So in NOvA, you see this beautiful, and the steel also absorbs. So this is the hadron shower here, not the lepton part. It would just absorb all this stuff before you could even see it. So Minos did most of its science just by looking for the muon track, which was longish, and that was it. That's all they could see. Now this event display is slightly different. In this one, by eye, I can't pick out a muon, so that makes it one of those neutral current interactions. It's probably pretty high energy because everything's so forward going. The interesting thing about this one is it's colored in charge. So the purple stuff is higher energy and the pinker, redder stuff is lower energy. And that's what we can use to identify particles by looking at how they deposit their energy. Hey, I guess I made it to the end. So I'm on time. So I will ask questions for as long as you guys let me, or I will answer questions for as long as you let me.
Because you get a quiz.
And yeah, no, that's not what I'm here for. And if you guys have to leave, that's fine. Is that an agreement?
Yep.
Okay. Questions?
So in something that's super dense, like neutron star or something, that would have like interactions between neutrinos really often, what would that do?
Well, no, that's a really interesting question.
Ooh, you didn't see that one coming.
In stars, yes, neutrinos should interact more often. I don't think that it's spectacular. What you might see is that a neutrino interacts and it produces, I don't know, some pions or something in a muon. But then the star is also really dense, and you know it's a lot more likely to interact? Those daughters. So what you're going to see is this neutron coming in, depositing some energy into the star. And then those daughter particles probably don't make it very far, and then they interact with some other neutrons. It might make some heavy nuclei, because you know stars fuse neutrons and protons to form nuclei. But it's probably at such a low level that it's not an, I don't know, I'd have to look that up. Maybe it's an important process in neutron stars, but I don't know a lot about solar physics, or what you call it, stellar physics. So anyway, now, but something I can tell you that's really interesting is that when a supernova happens, can someone tell me why a supernova happens?
It just gets.
A star collapses, and it's because it's starting to run out of fuel. So when stars get old, they start to run out of fuel, and the sort of photon pressure, the energy pushing out, is no longer enough to fight the gravity that's pulling everything in. Okay? So you have this star that there's not enough energy to push things out anymore, and all of a sudden it just collapses in. Okay? And then it collapses in, and then the energy density gets really high, and then it sort of bounces back out, and that's the supernova. The interesting thing about it is that when it collapses, there's all these particles colliding and things happening, and the light can't make it very far out because it just scatters off some other particle right away. It's so dense. And it gets, actually, supernovas get to a high enough density that even the neutrinos can't escape. It's, you know, the most dense material in the universe, other than a black hole. And actually, it's a black hole forming in some sense. Or in probably some cases. Anyway. And the neutrinos just start rattling around in there. And then when it bounces back, all of a sudden it hits a point where the neutrinos can escape. The light can't escape yet, but the neutrinos can. So the very first signal that something distant would see, the first signal of a supernova, is the neutrinos that escape. And then it keeps growing. And the light comes sometimes later. Or it comes sometime later. Okay? So there's a growing number of neutrino detectors in the world, and they've actually linked themselves into this network that looks for neutrinos and says, hey astronomers, we see neutrinos, a lot more than we normally see, and they're all coming from a certain direction. You should point your telescopes there, because you might see something. And that is called SNOOS. It's the Supernova Early Warning System, which is a great acronym. It's not NOVA like this NOVA, it's Supernova. That effort, one of the big people on it is this guy, Professor Salute, Alec Habig. NOVA's working on getting, actually the grad student that sits across the room from me is working on getting NOVA plugged into SNOOS. First to receive signals from SNOOS so that we could trigger and see a supernova. But if we get good enough at detecting supernovas, which might be a long shot, then we could actually feed information into SNOOS. The detector that's really good at that is IceCube. It's super cool. You think this is funny, and it is super cool. It's in the South Pole. It's 2.5 kilometers buried in ice. It's great. Okay. So they're really good at seeing supernovas, but we haven't had one in a while. We're due. Next question.
So as well as like particle interactions in that scintillator fluid, does that cause any sort of like noticeable decay of that fluid, or does that have to be replaced?
No. It will last the lifetime of the experiment. And yet, so the hadronic interactions could, you know, if a particle hits a nucleus and makes a hard scatter, and that can kind of change the contents of the nucleus, you know, but they're rare enough that it'll be as stable as any other thing that, you know, it sees cosmic background. The neutrinos aren't going to make a difference. The electromagnetic disturbance that we actually observe, right, the thing that makes the light, those are electrons. Electrons kind of swim around, especially in a liquid, and they can recombine. So that really just nets out, and you know, an electron might hop from one to another and be slightly ionized, but then it'll probably hop back later because things don't like being ionized. And the fact that it's a liquid makes that better. So the plastic scintillators would be, or any other hard scintillator, is going to have a bigger problem, because then you've got, you know, when molecules change, but they're locked in a lattice of plastic, then that can put stresses in there. This is a problem for detectors like CMS, because they have this scintillator buried in lead tungstate crystal, and crystals are really, they want to be really rigid in their structure, but then once you start putting charge in different places, it might put some breaks in there. There's parts of CMS that are being upgraded now, correct me if I'm wrong, and it's because they were just completely destroyed by the first few-year run. So I think the silicon tracker is pretty much useless at this point. That's the innermost part that sees the most radiation. And the crystals, they don't break, I guess, but they start to get opaque. So these, have you ever showed them one of the crystals, or have they ever seen that?
Not like a.
Nope.
Through a
They're
video.
these really heavy crystals. They're wild because they're doped with lead to make them more reactive, and to make them absorb more energy. Doped in science means you add some small concentration of something. So the crystals in CMS are doped with lead, but as they get pounded with radiation, they actually get opaque and they turn like yellow, and so they have to be replaced. And I think that upgrade is going to happen in the next LHC shutdown.
How did you end up on this career path, and what options do you have going forward?
I ended up on this career path because someone told me it was free. And no, so here's what happened. I was an undergrad and I loved my physics classes. I was actually studying to be a physics teacher, but at some point I decided I just wanted to study more physics. And so I left the School of Education at Wisconsin, where I did my undergrad. The education program is really restrictive and it requires a lot of time in education courses. And so after my, after my junior year, since my early years of college were kind of funny, I would have had to enter a 2-year program. It would have been 5 years. And in the 2-year program for education, I would have had to take just education classes, and I would have been done with science. And I didn't like that. So I decided to switch to physics, which would let me graduate in perhaps 4 years, which did end up happening. And as soon as I made that switch, I was like, well, wait, am I going to be employable? Actually, no, I didn't care about that at the time. I don't know what I'm talking about. But I did start to be, since I loved talking to professors, I started to be surrounded with science. And maybe one of them sort of offhand said, like, if you like this so much, have you thought about grad school? And I said, well, no. And then I started thinking about it. But I always told myself I can't afford this. Like, it's not in the cards. I don't come from a rich family. I can't just waste time in grad school. And then all this stuff. Oh, then I was talking to a different professor, and she said, I was like asking questions after a special seminar. And she said, do you need a job? Because we've got some openings this summer. So I started working on Ice Cube, which is a really cool detector. I did that for so that was after my sophomore year of college, that summer I started. I loved it. I started learning programming, which is what I do most of the day. So finding those neutrinos is mostly programming because you've got all this data. You got to make lines out of particle tracks and then learn something about them. I started doing that. I loved it. And then I was talking to grad students one day, and they're like, are you going to go to grad school, man? And I said, I can't afford it. And they said, afford it? You get paid to do this. And I said, free. And they said, yeah, we're all on fellowships, and we don't pay a dime of our tuition. I do pay student fees, but it's like a few $100s a semester. And I get paid. I don't get paid well. I'm not driving a Mercedes, but I can eat, and I've got a warm house, and a little bit of money to have fun on the side, and it's great. Now, I do look sometimes at some of my peers who are out in the industry, and they're making a ton of money. And I'm like, oh man, I've been in grad school for 5 years, and, well, I haven't. I've been in grad school for 4 and a bit of years. But, and then, you start to think, like, I'm ready to move on. But that doesn't mean I don't cherish every minute of grad school, except for the ones where I was working 60 hours a week or more. Okay. So anyway, so that's part A. Part B is what do you want to do after? It's common for physics PhDs to do one of three things. One is become a postdoc or a postdoctoral fellow or postdoctoral research associate, whatever you want to call it. That means that you have your PhD and you're still doing science. You're like a grad student, except you hopefully know more. And if you do a couple of those and they go really well, then you can end up being a faculty at a big research institution like the University of Minnesota or anywhere else in the country where they have tons of state money to spend on science. But it's sort of a pyramid scheme, right? Because there's not a lot of faculty positions and there's a ton of grad students. Well, and no, so I say that because there was recently a bit on NPR about this new age pyramid scheme where you're rewarded with education, and it's called postdocing. And I was like, whoa, that's what you're talking about? I don't know. It was, they were being all expose about it, but it's kind of the fact of the matter. Now, in the sciences, it's better than other places, and less mean and competitive in physics than maybe pharmaceuticals, but it is all the same. Now, so that's one thing. You stay in the research track. Another thing you can do is, if you like teaching, is go on to be a professor at some smaller college where they don't do research. Maybe you do a little bit, and that tends to be less competitive because more people want to stay in science. And the other big thing, which I think the field is struggling with right now, is that you can go into industry, and there's tons of people who like hiring physicists because they're good at understanding data and they're just good at solving problems. And when you hear about big data from companies like Facebook and anything else that's connected to the internet and constantly collecting data, they need people to study that data and sift over it. And they pay a lot more, and it's a lot less competitive. And in the past year, I've actually thought about doing all of those things.
At once?
No, I tend to shift. But lately, I find, and a year ago, here's where you catch me in double take. A year ago, I said that going into industry was soul-sucking, and I might have told you guys that I was now thinking about being a postdoc. And the year before that, I said I definitely want to teach when I came here. And now I'm in the industry camp. I want to go off into industry, and there's actually really interesting problems to solve. And I've found that I like computing more than I perhaps like science. So I might want to flex those muscles more in the future. So there's a lot you can do if you get a PhD in physics. And that's just like the common things that I listed. Other people go into finance and work on Wall Street.
When even backing up to the undergrad, and even getting an undergrad in physics, a lot of people don't necessarily work directly in the field of physics once they get that degree. And so you're very marketable with a physics diploma because of what Dominick has been saying with your problem-solving skills that come along with that, etc. So
yeah, physics kind of teaches you to flex a lot of different mental muscles, and it teaches you to take some knowledge from over here and apply it, with some knowledge from over there and combine things. Synthesize, if you will. I recently heard Garrison Keillor say that when I was a kid, 2 + 2 was 4. It couldn't be anything else. There was no such thing as synergy. Anyway, but now there is. Companies are looking for synergy, and they're trying to take different pieces and put them together. Physics does prepare you to do that in a sense, and I would have been employable coming out of school, but applying to grad school was the path of least resistance at the time. It's something I really wanted to do.
Do you have health insurance?
Yes, and it's one of these Cadillac health plans, and it's super cheap because it's subsidized by the university.
Oh man.
Yeah. My girlfriend works in a hospital, and her health insurance is terrible compared to mine.
I have an important question. Do you believe in anti-neutrinos?
Yes, absolutely.
They exist?
Absolutely. Antimatter exists. It's well established.
Well, no, but
It's not a belief question.
But no, I thought the definition of antimatter was it was an oppositely charged particle from what is normally recognized. So like a positron and electron.
Okay. So the question, can I restate the question? How do you have an anti-neutral thing?
Yeah.
Okay. For neutrinos, the difference is that an anti-neutrino produces an anti-muon, or a mu plus. Okay. So you can observe the difference. Now, there are theories that say maybe neutrinos and antineutrinos are actually the same thing. The difference then that allows them to communicate muon or anti-muon would be something about the spin and the chirality, and it would be that since they're, you get into how the spin aligns with the momentum when they're going really fast, and since they're so light, they're always going fast, except for the ones left over from the Big Bang, but anything we see. And so antineutrinos stay antineutrinos because of the way their spin aligns, and it gets gray. But antimatter is well established, and you can have an anti-neutral thing.
Okay. And I have one more question. Sorry.
I'll get back over here.
Sorry. Do you believe in the supersymmetry thing?
Susie, they call it, supersymmetry, is almost dead. The LHC is in the process of killing it.
Oh,
There are bits of phase space that would still allow. So you kill a theory like that by looking at the things it predicts, like particle masses and interactions, and from the things you measure, like the mass of some particle, I don't know, they measure this stupid thing like the mass of the neutralino versus the mass of the stop. And the stop and the neutralino are things that they measure, and through certain interactions they can sort of try to get at the masses of those particles, right? And so what they measure, they look at, I'm going to try to go really quickly through this, but you can make a plot of, let's imagine a universe where the mass of the stop and the mass of that other thing, the neutralino, imagine that they were blah blah, you know, this mass and that mass. Okay. And then they take their data and they fit it assuming that. And they look at how well it fits the data. And if it's a good fit, it's allowed. If it's a bad fit, it's not allowed. They do this over the grid. Okay. And there's like a region over here where it's a good fit, and maybe a region over there where it's a bad fit. Well, if you look at this plot, and it's all plotted on log scale so that you span like every possible mass and every possible mass. And if you look at it, and you know, the limits on your scales is like what the theorists say it could possibly be. So at some point it's just ridiculous and you know, it doesn't matter anymore.
Yeah.
And if you look at it, like the plots kind of look like something like this, where all of this is excluded and there's like, and all of this is excluded, and there's like little patches of phase space. That's what you call this. Like one of these maps, you call it phase space. There's little patches of phase space where Susie could still exist, but it's starting to look pretty grim. So, and these things are called contours, contour plots, and you separate the bits of phase space which could describe reality from the bits of phase space which couldn't. Well, yeah, so I kind of said that, you know, when charged particles are moving quickly through some material, whether it's you or me or that table or liquid simulator, they'll ionize. So, you know, you'll come through and it's really simple to work out how particles deposit their energy in a sea of electrons. And that's what everything is a sea of electrons with some nuclei, right? And the nuclear scatters are rare, so with very basic physics, you can work out that when particles are moving really slow, they disturb the medium a lot because they spend a lot of time near the nucleus. And as they start to move quicker they sort of get in and out of there, and they disturb the electrons less. And then as you get to really high energy or velocity, they're the same thing. Then you start to become very relativistic, so you actually, from the lab frame, they spend more time near the nucleus because they're going faster, but we see them as slightly slower than they would be going. And so they spend more time in the near the nucleus, so they start to deposit more energy. And that makes this sort of what they call the beta block dE dx. If you know calculus, it's a derivative, and it's bit of energy per bit of path length that the thing traverses. And you make this nice curve. I'm drawing it backwards for your sake, but it's really high at low. If you draw dE dx versus velocity, it's really high at low velocity, and then it has this minimum. The muons we observe happen to sit close to that minimum. And then you get that relativistic rise out here. And so that energy deposition and how much you deposit is actually how we know about the particles. You know, how we can tell a pion from a muon because they sit at different points on that curve. And to answer your question more directly, which was how does it work? When those electrons are disturbed, and maybe they're moving around, they want to recombine with an atom or make some atomic transition to get rid of their energy. The thing that makes the scintillator special is that it has allowed atomic transitions which are visible light, right? So you make this hop down and it emits some visible light.
So there's just like a physical flash of light inside the later, and the map picks it up.
Yes, and transmits it to the image.
So then how do you map it? Because it's so long.
Right. Oh, so you don't. So that's a really important question. You don't know how deep in that cell the interaction happened. All you know that it hit that cell. You need the other view. So if it happened in a horizontal module, you need the adjacent vertical module to tell how deeply it happened. So NOvA has two views, each with 3 well-measured coordinates. Z and time are well measured in both views, but in each view you only get X or Y.
And
Now-
Minos does the same sort of thing, just with the, I believe, isn't it? With the every other
Yeah,
layer of
Minos,
simulation.
yeah, except in Minos they're not actually X and Y, they're U and V, they're like a
Yeah.
skew. That's why Minos is a hexagon. And so that's why everything we do, we can't really make a 3D event display. We can just have two 2D event displays. Does that answer the question?
Yeah.
Should I allow a mass exodus and a lot of you to leave? And
Yeah, let's
anyone else?
do at least one. If you have more questions, certainly stick around. I want to apologize. I don't know, some of the pop that I got went somewhere that I don't know if someone stole it from sitting outside. So if you went thirsty, there's water and there's a little bit of pop left. And I'm sorry about that. I had more, but thanks for coming. Again, stick around if you have more questions. But let's let one get a question. Sure.
Oh my god, I don't want to go home and I have to do homework. You know, I don't know where to go on that. I don't want to finish
Get my $5 worth of cookies.
I'm looking forward to having something to have probably going back to right now. So I'm looking forward to I'm kind of going to have all my medical problems now. That's a good
For me, before just talking to someone. That was
He's very good. They just arrived today. Yours are going to Master Harold tomorrow.
Thanks, though.
Still have them.
I have an account on Cosmic
You paid $5
I just like asking people what they think about gravity. Yeah, let's go take more food.
So the time
I'll
think that works. Yeah.
One cheese.
My last name, Rocco.
Is there any pizza?
I think these are all empty.
There's carrots.
So yeah, sometimes I'll just redirect you to, you know, like maybe a student grade office where they might be more. And I'll add as soon as I.
No, don't take it. What's these? When you turn the motor,
You know, that's the same procedure. So you're getting involved now or later in college? Yeah,
there's like a ton on that.
they might know. I don't directly know, I just know that I have some.
You get a new 9 volt, you stick your tongue on it, you'll feel it.
I somehow had